Hello everyone, I'm Charlie, and in this video I will go over the second article of my thesis called Combining Supervised Learning and Local Search for the Multi-Commodity Capacitated Fixed Charge Network Design Problem. This paper was published in Transportation Research Part E, October 1st, 2024. This paper is mainly about the fixed charge network design problem. It's an influential NP-hard problem that has been studied for decades, and there are a wide range of applications, so it's very relevant in many domains. It has a similar structure to the LAP, where we have binary decisions on every arc rather than a consist assignment. At a high level, the network design has two main types of decisions. We have fixed installation costs and variable routing costs. The fixed costs are associated with the binary variable y. These are the design variables, and most of the difficulty comes from optimizing these variables. Whereas we have also flow variables, these are continuous variables, and once you have the correct set of binary variables, it becomes easy to find the corresponding um, flow variables. We also have constraints modeled by UIE on every arc. Our methodology is based around supervised learning, where at the beginning of the procedure, line 2, 3, 4, 5, we collect samples from the instance, and we use those samples to first get a good solution, but also as features that we push to the ML model to get an estimation. These estimation and the best feasible solution found so far are used in this solve function to search effectively around what solution we predicted. Our method is based around the state-of-the-art local search heuristic, which we refer to as LS star. This method was developed by Katayama 2020, and in this research we reuse the same code as Katayama as for our baseline. This heuristic has two main types of constraints. The first one forces the solver to close at least one arc, and the other one defines a neighborhood of size m. We use sampling routines to generate useful features. To do so, we use randomized slope scaling and local search file sampling, which is based on capacity scaling. These methods, you can think of them as specialized heuristics of algorithm for the network design. They're very good at finding rough approximation of good high quality solutions, and they're very fast. We use those to generate features, and these features are used as input to our ML model. The training process is straightforward. We take advantage of the standard supervised learning framework, where you have some set of features and a label. In our case, the label is the best solution we have so far for that instance. And we optimize the cross entropy loss, which is standard for a binary variable. We also include omega 1 and omega 0 to tune the balance distribution of every class, because we're working with an unbalanced data set here. We're working with two different data sets, GT instances. These are used in the original work of the Katayama, and we have generated instances. They are produced using a modernized version of the Canad dataset, and here's the statistics on them. We have grid and circular topologies, and we have our test set, which is 30% larger than our training set, to test the generalization properties of our model. Here's some data about the model tuning. We tried different models with different set of features. The main takeaway here is the substantial improvement from sampling features. So you can see that here we have sampling and sampling features, and we have no sampling features. And when we add the sampling features, we get from about 68% accuracy to above 90% accuracy, validation accuracy. Whereas the other features, such as basic features and node features, do not contribute meaningfully to the ability um, of the model to predict accurately high quality solutions. We did some algorithm design analysis. We tried different ways to integrate the prediction in the local search algorithm. Here, the key takeaway is only LSR can outperform LS star if error rate is below 10%. So we found that this method here, where we remove from the graph the arcs for which the ML model predict that they should be closed, if we remove them, this is the method that's most resilient to noise and gives the best performance overall compared to using a local branching scheme. Here's some results. These are gap. So lower is better and represents the quality of solution that we find. The results on GT instances. So we can see that, for example, our method LSR, and we use LGBM as the ML model with different bias weighting. So the non-biased version gets about 9.4, whereas the biased version towards the negatives gets 5. And the bias in the other directions gets 14.7. So we see a meaningful performance upgrade when we bias the model in the right direction. This is because our dataset is unbalanced. However, our balanced model do not outperform LS star, because LS star was explicitly tuned on GT's instances. We also experimented with another dataset. So here is the result for another dataset. In that case, we do outperform LS star with our best model. No, it seems to suggest that our method does work well, and we seem to outperform the state-of-the-art LS star on instances that was never seen before by the state-of-the-art. Notice also that we find solutions very quickly in the solution process, whereas LS star takes a long time in the beginning to do pre-solving steps. So there's no solution found after 1800 seconds. In this paper, we propose to combine supervised learning and a state-of-the-art heuristic. We tried different ways of integrating them, and we found that the best way is to remove the arcs from the graph. Sampling features are very informative, and they give you way more information relative to static graph features, such as node graph features. Also, our results suggest that it's most effective on instances sampled from a uniform distribution. So thank you for watching. Bye-bye.